Have you ever wondered how an AI can look at a picture you drew and instantly turn it into working code? Or how it can create an inspiring song from a simple text description? That's the magic of multimodal AI models. And in this video, we'll dive into exactly how these powerful tools understand and interact with our world. Welcome to AIClubPro, where we make AI concepts sound like everyday ideas. In today's video, we'll look at how the large language models are able to accept inputs and create outputs both in different modalities like text, images, etc. We'll look at the difference between multimodal interfaces versus multimodal models and some examples of each. Multimodal models are AI systems that can process and generate multiple types of data, like text, images, audio, and even video. Instead of being limited to just one form of input, such as text, these models can seamlessly integrate various data formats to give you the outputs that you want. In our past videos, we looked at the transformer architecture, the large language models, and vision transformers. However, all of these models were designed for a specific type of input, either text or images, and produced a specific kind of output, like text or a category. So how does a model accept more than one modality as an input? If you're familiar with the transformer architecture, you know it comprises of an encoder and a decoder. We'll answer what components of this architecture the multimodal LLM uses. Typically, the multimodal models can use either just a decoder, just an encoder, or both decoder-encoder. So let's start with decoder-only models first. Decoder-only models rely on turning every input, no matter what the type, into a single unified language, which is embeddings. When GPT-4 receives multimodal inputs, each input modality, whether it's text or an image, is first converted into what we call an embedding. These are the numerical vectors that capture meaningful information. For text, this is usually done by directly tokenizing the words and mapping them into embedding vectors. For images, GPT-4 employs a specialized image encoder, often something like a vision transformer, to generate these embeddings. Once both modalities are represented as embeddings, the decoder-only structure takes over. Using self-attention mechanism, GPT-4 examines how each embedding relates to all others, enabling the model to understand the context across different modalities. This means it can integrate insights from both text and images simultaneously. By converting multimodal inputs into embeddings and processing them within a unified decoder structure, models like GPT-4 achieve remarkable versatility and coherence, even without a traditional encoder-decoder pair. So let's look at encoder-decoder models. So when both encoder and decoder are present, how would multimodality work? So this architecture is especially popular for tasks like image captioning, video summarization, or turning audio into text. And here's why. Encoder-decoder models handle multimodal inputs by splitting the processing into two clear stages. First is the encoder, where the model takes complex inputs like images, videos, audio clips, etc., and transforms them into condensed, meaningful representations, which is embeddings again. And you can think of this step as the model summarizing everything that's important into a compact and precise format. And then comes the decoder, which takes these embeddings and produces the final output. The decoder uses something called attention again, which enables it to selectively focus on different parts of the encoded embeddings at different times. It's like the decoder is continuously glancing back at the key points that are highlighted by the encoder. This makes sure that the output stays accurate and contextually coherent. This two-step approach, encoding followed by decoding, makes the encoder-decoder model particularly effective at generating structured, meaningful outputs from complex multimodal data. So lastly, let's talk about encoder-only models. In encoder-only architectures, separate encoders process each modality independently. So one encoder specializes in text, another is dedicated to images, and so on. Each encoder translates its input into numerical representation, which is, again, embeddings. But how exactly do these embeddings end up aligned? During training, models like CLIP learn by comparing pairs of images and text descriptions. Specifically, the training involves huge data sets, which are pairs of images and the corresponding description in text. So this is matched image caption pairs. The encoders adjust their internal parameters to ensure the embeddings of matching pairs of image and text end up close together, while embeddings from mismatched pairs get pushed apart. To achieve this, the model typically uses a contrastive learning approach, which is a fancy name for a training strategy where it explicitly encourages the embeddings of related inputs to be similar. So in the vector space, they're closer in distance, and embeddings of unrelated inputs are, far from each other in the high dimensional space. Through this iterative learning process, the text and image encoders gradually become synchronized. Ultimately, this allows the model to directly compare embeddings from different modalities, letting it match images with relevant captions or identify textual descriptions that closely identify the image. Such models are widely used for tasks like image retrieval, zero-shot classification, content moderation, and enhancing accessibility tools by matching visual content with matching text descriptions. Now that we have gone over how input can be of so many different forms, let's look at how the AI models take this understanding and use it to generate outputs that are across different modalities like images, audio, or videos. Once an AI model encodes and grasps the meaning behind your input, it has a structured representation, which is again the embeddings, which captures the semantic essence of the information. These embeddings essentially serve as guides that inform the AI on what kind of output to generate. So let's peek under the hood to explore the architectures that make this possible. Just like transformers have key components like the attention mechanisms, positional encodings, and feed-forward layers, generative models also have their distinct building blocks. So first up, let's discuss diffusion models, which are behind the stunningly realistic image and video generation. So typical diffusion models have the following core components. They have something called a unit, where you can think about it as a neural network which is U-shaped, and there is an encoder. It compresses, this is a different encoder compared to transformers. It compresses the noisy input images into a high-level abstract representation. And then there is a decoder, which is also different from the transformer decoder, that reconstructs this representation back into noise-free outputs. And then there are residual blocks, which are skip connections that help with training. And then there are attention modules, which are inspired from transformers. These modules help the model to dynamically focus on specific details within the input, resulting in a sharper and more coherent image. And then there are conditioning mechanisms, which are super important. What they do is they accept the embeddings from the input, such as text descriptions or even another image, And then they basically take these embeddings and use it to guide the image generation process. This ensures that the output matches exactly what you're looking for. Recent advances in models like Google's Imagen 3 or Veo 3 have extended diffusion architectures to handle ultra-realistic 4K resolution videos and even synchronized audio, introducing advanced temporal attention and sophisticated multi-stage conditioning process. So another architecture in the generative process is the GANs, Generative Adversarial Networks. This is something that consists of two neural networks that are locked into competing with each other. So there is a generator network that transforms random noise or conditioning inputs into realistic outputs, like convincing images or synthetic audio. Then there is the second neural network called the discriminator, which evaluates the generated outputs that was generated by the generator, and it classifies them into real or fake. So this constant feedback from the discriminator pushes the generator to produce increasingly realistic results. Another powerful architecture is the autoregressive model, like GPT for text or WaveNet for audio. These models generate content sequentially, piece by piece, considering the previous outputs to determine what comes next. So they have a causal self-attention or a convolutional layer, and these layers attend to the sequence generated so far so that there is consistency in context. And then there are positional embeddings, which are essential for maintaining order. They tell the model exactly where each part belongs in the sequence. And then there are output prediction layers, which convert the hidden states into actual tokens or words in sentences or pixels in images or sound samples in audio. Lastly, let's talk about variational autoencoders. VAEs operate by compressing and reconstructing data through a structured latent representation. So again, they also have an encoder network which compresses the input like images or sound into a compact, meaningful representation. And then the architecture is typically quite different from what you see in an encoder in the transformer though. And then there is a structured low dimensional space which is called the latent representation, and this allows easy and controlled sampling of new data. And then we have the decoder network that reconstructs new realistic outputs from this latent space, and that enables creative variations and realistic synthesis. Now that we have gone over the architectures which accept different modalities of input and generate different modalities of output, let's see these multimodal architectures in action through some examples. Consider the scenario where you quickly snap a photo of a handwritten note or a sketched web page layout, and then you send this over to something like GPT-4, an AI. So here an encoder-decoder model shines. The encoder first analyzes your handwriting and extracts meaningful information into embeddings, and then the decoder steps in and translates these embeddings into precise editable text or HTML code if that's what you desire. So it captures your original intent in a structured format. Another example is where you could describe your ideal music style. Let's say a calming piano melody for relaxing at sunset. In this case, a generative model like a diffusion model or autoregressive model will take the text input and create an embedding that conditions the generation process. Using these embeddings, the model generates a completely original piece of audio that aligns with your envisioned mood and style. So these examples just show us how different multimodal AI architectures, each using embeddings and specialized processing steps, enables seamless transition between different inputs and outputs of different modalities. Now here's an interesting nuance though. While interacting with an AI system like a chat GPT, everything may feel seamless, like you're talking to one incredible versatile AI that understands speech, text, and can even generate images. But what's actually happening under the hood could be quite different. Often the system you're interacting with isn't a single multimodal model at all. It's rather a carefully orchestrated combination of specialized AI models that are working together. For example, when you speak to ChatGPT, it may use a dedicated speech to text model like Whisper or convert your voice into text. Next, GPT-4 may step in to understand the text. If you're requesting an image, maybe a separate generative model such as DALL-E creates the visuals based on the input provided by GPT. Even though the interface you interact with appears unified and fluid, behind the scenes it is a coordinated assembly of many powerful models, where each model is optimized for a specific task. All these models collaborate seamlessly to deliver a sophisticated multimodal experience. So, in summary, a multimodal framework such as this is quite different from a multimodal model. And understanding multimodal AI helps us appreciate how these powerful architectures transform these simple inputs into extraordinary creative possibilities. So that's a wrap. Thanks for joining us on AIClubPro. Hit that subscribe button for more eye opening AI insights. Stay curious and keep exploring.